Good morning, mathematicians. Oh, I don't even have my microphone set up. Brutal. I think I forgot that the other day too. I noticed the audio sounded significantly worse. Um, so let's fix that problem now. Let's see. Is that yeah. Now you can get the full coffee drinking ASMR experience. See, aren't you happy that you had that instead of my computer mic? ASMR experience. That's what you all come here for, isn't it? Good morning, Russ. Good morning, Russ. How's it going? What are we going to get into today? That's the question. Do you kind of want to make... Yeah, I have so many video ideas, but just no time. I gotta get these papers written. And then I gotta get applying to postdocs. Maybe we could search math jobs together this morning. Yeah. Let's take a look at math jobs. Let's take a look. Anybody saying Langland stuff? No, of course not. What about number theory? Okay. About the same amount of hits as before. Algebra? There's a lot of algebra. So that's probably what I should do. Probably gonna quit your job to study math? Well, I would say make sure you have some way to make money. But I mean, that would be the dream. As I've said before on this channel, if I could go back in time, I would have been a quant and then made bank and retired 3 years ago, and then just spent the rest of my life studying math. I mean, inevitably, no matter what happens to me, I will spend my entire life studying math. It is just inseparable from who I am as a person at this point. So the question is just whether I'll be a academic or not. Oh, you do tutoring on the side. Well, there we go. The great tutoring chain of tutors. I wonder if you tutor someone, does that count to get added to the mathematics genealogy project if they get famous enough? No, I think that's strictly for PhD supervision. There is a lot of hits for geometry, though. Yeah, I guess I should start applying everywhere where I see that. Right? That makes the most sense. Let's see. About Canada. University Ottawa. Math is life. That's true, Conan. That's true. Math is life. Speaking of actually talking about math, what should I yap about today? We were talking a little bit about extensions and stuff last time, but I'm not really prepared to go into any more depth about it. as opposed to last time. I did never finish yapping about some of the graph theory things that I started my old research. Yeah. Although, does that matter? So maybe just as a reminder, maybe I'll start talking about that. So if you have a graph G, you define a polynomial. Define a polynomial where the coefficient of it should be the coefficient, so n is the order of the graph, and the coefficient is the number of connected induced subgraphs of the graph of order I. And previously I coded, I think I showed on screen last week or so, some different distributions of those numbers of graphs. And they all seem to have roughly the same structure, but it could just be a consequence of looking at graphs as small order. And the question is, which graphs have minimal structure? So conjecturally, paths. Paths have minimal mean, so that is can be obtained by taking the logarithmic derivative of the polynomial and evaluating at 1. Happens to be equal to the mean. And so, okay, what's a strategy for proof? So I think it was Jameson. I could be misremembering. Again, it's been many years since I actually looked up any of these papers, but I think it was Jameson who originally proved that paths are minimal among trees. Maximal is still open. And in fact, I don't think we even have a good guess for what is maximal. Well, I'll tell you what they seem to look like. Here's what I tell you. Here's what maximal trees tend to look like. Something along the lines of this. And what's weird is, can I explain what sheaves are? Well, I could explain it here, but I actually have a whole series on sheaves. I have an entire series. I have like 17 videos. Or something like that. I have this whole playlist here. So I will maybe, I mean, not that I'd be upset about, I'd be happy to talk about them in office hours, especially if you have questions and stuff. But maybe I would first direct you over to the series. 17 videos. Definitely, this is not a complete series. I've wanted to make more, but I'd direct you here first. Maybe this is a good place to go get a first introduction. Yeah. Gotta pause the group chat. So, coming back to graphs for a moment, maybe I'll talk. Maybe I will end up talking about sheets later in the episode, but just for now, yeah. Since I have the pre-recorded videos, I'll yap about some other things, and then maybe if I get to a stopping point, I'll yap about sheets later. But um, the point is that they sort of look like this. The maximal, I think if I'm remembering correctly, these even seem to be maximal among all graphs. I could be wrong, but I think these might even. But this is purely just computational. This is what they seem to look like. So it's interesting that yeah, the shape. So like it's very path like in the middle, but I guess there's a lot of these like things on the end, right? So if you think about it, it is forcing quite a few large order graphs, right? So something like this, right? That's you're accounting for, and then you toss in a couple of these in the middle. You're accounting for quite a few. That's driving up the number, and you just switch between these edges, and that's giving you a lot of large order connected induced subgraphs. But the weird thing is, secondly, is like there's these little tendrils in the middle that pop up. And the thing is, it's not even clear what the pattern is of how they show up here, right? Because you see the way I've drawn it here, like it's not symmetric. And I'm not saying this is the maximal one, but as I recall from our computer searches, when we went through the trees, you look, you see it, you get a bunch of graphs like this, right? They've got a bunch of these things on the ends, and it seems to be fairly spread out. But there just doesn't seem to be much of a rhyme or reason as to why these are here. And the immediate thing I remember thinking, I'm like, oh, well, okay, the computer returned that these were maximal, but are there more than one maximal? Like, are there several different graphs that achieve the maximum? And the answer is just no. It doesn't. There doesn't appear to be that much of a pattern. Sorry. The answer is there's always seems to be a unique graph which has the maximum, and there just doesn't seem to be any rhyme or reason to the distribution of these little things in the middle, which is interesting. So here's an open problem for you, by the way. Here's a very, I don't know, well, definitely it's not easy, and so not approachable in the sense of like I don't even know how you'd begin to prove it, but it's definitely something that's easy to draw and make pictures of, and to write Python code to test stuff. Yeah. So that's that. My research was on proving that paths are minimal among block graphs. And a block graph, okay, there's some fancy definition, but roughly what it is you take a bunch of complete graphs, and you glue them together in an iterative process. So what do I mean by that? So of course the sequence continues. But what do I mean is that basically you take two complete graphs. So let's take a complete graph on 4 vertices, and then you can glue one vertex to it, right? And then, so this would be a complete graph on 4 vertices glued to a complete graph on 3 vertices. But then I could glue like another one on 3 vertices, or here I could glue one Maybe, so to that same vertex, I could glue another one on 3 vertices, or I could glue one on 5 vertices, or they don't all have to be, that should go there. That should go there. That's drawn very sloppily. And then, okay, here's a complete graph on 2 vertices, and then another one on 4. And the thing is, notice that you'll never make, of course, the graph has many cycles, but you'll never make like a loop of block graphs because you're never gluing 2 vertices at once. So this is what a block graph is. And so we managed to prove that paths are minimal among block graphs. So how does that proof work? By the way, this generalizes the result from trees, right? Because what is a tree? It's just you've glued a bunch of complete graphs on 2 vertices. Can I teach from basic? I'm not sure what you're asking. Good morning, Arad. Like, you want me to, in terms of this, are you asking in general? Like, do I teach basic math in general? Yes. Or are you asking for the basics on this particular topic? If you're asking for the basics on this particular topic, then this was in, I did cover more elementary aspects of it in previous office hours. But yeah, if you can clarify your question, then maybe I could give you a better answer. So, trees are special cases of block graphs. So there's a couple different lemmas here. So one lemma basically says that, imagine you have like, here is, do I do real office hours? What do you mean by that, Nerdy Quagsire? If I have 2, so here there's like one block, right? And I have 2 sort of paths leading off of it, right? That are attached to distinct vertices. Then there's a theorem that basically says you can imagine sort of pulling that path sort of like through here. There's a theorem that says if you sort of move that path along, so it becomes this path, so you have a graph of the same number of vertices, but you end up decreasing the mean. So likewise, let's say just as an example, say we just had a thing that was like this, and let's say we had 2 paths. Okay, those are different vertices, but so there's, as you might imagine, there's results for the same vertices as well. So here's sort of graph 1, and again, this is totally balanced, so it doesn't matter whether you go to left or right, but you can imagine sort of like pulling the path along this way is the way to think about it. So you sort of imagine at the next snapshot, we've moved it, we've sort of pulled one extra vertex this way. So this would be like the next snapshot, and the next snapshot after that. And then finally, we would have fully unraveled the path. 1, 2, 3, 4. And there. And so the claim of the lemma is basically that each of these, the mean between each of these graphs is, well, in fact, I think you could prove it's strictly decreasing, but we just prove it's monotonically decreasing. And like I said, there's also a version where the two paths coming off an end meet at the same vertex as well. But what's really cool is the way that we prove it is, well, it's math, nerdy Quagsire. All questions are done. Or none of them. I still can't make up my mind, but it's one or the other. Well, it won't be strictly decreasing because, of course, if you get to this, right, if you get to like here, this will be like some sort of saddle point. But no, I think it is. If you had an odd number of extra edges in this example, one could do one step and get an isomorphic graph. Oh, sorry. Yes, that's true. Sorry. Yes, that's right. A new paper on archive on it. Oh, let's go and take a look in a second. It is somewhat relevant. Directly relevant to my research, no, but I'll say some things on it in a second. I wonder if that was Rosenblum, Nick Rosenblum, because I think, well, I was at a conference in the spring and he gave a talk on something that was had to do with like finite fields Langlands. But let me just finish one thought here. So the point is that the way that we do this is well, we basically have these graphs that depend on a parameter t, right? And so the way that we set this up is that t basically tells you which vertex, right? So if we label the vertices, t could be a number from 1 to n. And then, as Arad mentioned, though, of course, it will be, the graphs are isomorphic, right? Like if you just swapped both of these two branches, it would be isomorphic. So really, you can view it as like t is from here to maybe floor of this, right? So t now is an integer, right? So we get an integer sequence of graphs. And so, we have their means. And so you can just work out some function. You get some formula which depends on, now the graph could be bigger than this, right? There could be more stuff going on here. So you end up getting some function that sort of depends on the mean of the graph. I'll write g minus p for like the rest of the graph without this path, and then you have the part that like depends on like this path component. And I can talk later about exactly how you decompose how you relate the means to each other. But so the interesting thing is what you can do is you can forget that this has anything to do with graphs, and you can just view this as a function, and then yo Naja. And then you can just view this as a function of the variable t and pretend that it's a continuous variable in this interval. And then we just use basic calculus is that we show that the derivative of viewing this as a function of t, we just show that it's less than or equal to 0. And so therefore it's monotonically decreasing as t increases. And that gives the result. Or maybe I don't remember which way we wrote t. So maybe t goes down to here and then the derivative is monotonically increasing or whatever. But however we formalize it, yeah, we basically, even though this is a totally discrete problem in graph theory, we use calculus, basic calculus, to prove it. Yeah, so actually, I mean, the more I'm thinking about it, directly, Langlands for finite fields isn't directly, say, useful for my thesis or something. But one point of contact, and I don't know if like the Langland's program for finite fields embeds into this, but there is a point where the finite fields are very useful. So in previous videos, I've talked about how, well, for any group, but say for GLN, there's a classification of all the representations in terms of multi-segments. Hey, Jeffrey. Good morning. And those multi-segments are what? They're basically combinatorial gadgets where you have a choice of something that's called a supracuspidal representation. And then you have some what are called twists of it, but whatever. That part is basically just good question, Arad. We should go to archive and look at that soon. And so you basically just have collections of these things. And so the point is that if you black box the theory of supracuspidal representations, then you get a complete description of the representations of your p-adic group. Okay, and that's fine. That's how I first learned it. But then what if you don't want to black box the supracuspidals? What if you want to know what those are? Well, how do we build supracuspidals? As an example, one way, there's a whole very interesting industry, which I'm very ignorant of building supracuspidal representations. But one thing you can do is say, if we're looking at like GLN QP, you take GLN ZP and you get a projection from here to GLN FP over the finite field. What time do I usually stream? What is my schedule? Thanks, Lara. I did trim up the beard a little. I don't have a set schedule, which probably would be better for like engagement or whatever if I did. But generally, I start streaming sometime between 7:30 and 8:30. That's pretty typical. What you do is you look at you choose a Borel subgroup. In GLN FP, and then you take the inverse image of the projection map, and that's what's called the Iwahori subgroup. This is the Iwahori subgroup. There's other better ways, there's better ways to construct this, but to be more precise and rigorous and careful about things like algebraic groups and choices of models and things like that. But you look at the Iwahori subgroup, and apparently one way, so if I understand correctly, there's also a notion of supracuspidal representations over finite fields. And so what you can do is basically take one of these representations down here, pull it back to the Iwahori subgroup, and then so you let that be like the pullback to the Iwahori subgroup, and then you take the compact induction from Iwahori up to your group, and apparently this thing will contain supracuspidals. And I think maybe even for GLN, you can, like, most of them appear in this way, or all of them or something, but I don't think it holds in general. Yeah. Do I have any suggestions for self-studying mathematics, especially about choosing exercises? You always have an issue of making a choice of exercises to do before moving on to the next section. Yeah, there's just no good way to answer this. It's a very difficult problem. Yeah, I would say, look within yourself and be honest with yourself. And if an exercise scares you, or you feel unprepared for an exercise, that is a good sign that you should do it. Right? If you look at an exercise and you think it seems kind of, you're like, I could write that out, no problem. I mean, you would be surprised, and so I would say maybe do it anyways. But be really honest with yourself and say, oh, if you look at an exercise and you say, oh, is there a part of me that's adverse to this because like I don't I don't feel like I can do it, then that's a good sign that you should do it. That's one aspect of mathematical maturity. Yeah, which parts are the meat and which parts can be glossed over. Yeah, so I don't think there's a good algorithmic way to decide such things, but that's part of the point of having mentors and taking courses and stuff, is that you sort of, they will hand pick problems for you. Oh, is this first one here? Is this from the 20th? Yeah, they will hand pick problems for you that they think are the most relevant. But that can also be a reflection of a bunch of different things, including a reflection of how they view what they want to highlight or whatever. Yeah. By the way, Ravi Vakil's book, where you keep bugging me to buy it, you should buy it, or just look at the free PDF. The exercises there are very well labeled in terms of, oh, this is an important exercise, this is a non-important exercise, or this is a hard exercise but a good one, or like this is just sort of a fun exercise, not that important. It's all very well labeled. So we construct Langland's correspondence for connected reductive groups over finite fields, which we call the finite Langland's correspondence. Interesting. Who's this by? I don't know that name. Bro, you're poor? Okay, well then just download the PDF. Just download the PDF for free. Good morning, Julie. We formulate the Langland's correspondence. Interesting. Yeah, I guess I'm actually very ignorant of this, and I'd be interested in how this is supposed to interact with other components of the Langland's correspondence, like what I mentioned, right? Like, certainly there should be a way to relate supercuspidals. You already have the PDF, so goated, yeah. Well, start doing exercises. Is anyone here into lean? I think there's people into lean. I've spent some, it's been a while, but I had previously spent some time into lean. I think Nick is interested in lean. What's the intuition about these reductive groups? They're just, they're like GLN. Yeah, exactly. Yeah. I mean, one would, hey, it would be great. It would be great to just be like, oh, here's an algebraic group. Assume G is an algebraic group. Do some like Langland's things, but it just doesn't. Yeah, I mean, non-reductive groups are weird and messy. Although there's cool things for like, the orbit method does apply to like a bunch of nilpotent groups. So. Read a bit about it today and found it quite interesting. So I shill this all the time, but you should go check out Natural Number Game, the Lean Game server. You should go check it out. So you can play. Yeah, there's the Natural Number Game. There's Knights and Knaves game. Interesting. That I think is a new addition. But yeah, so you can go online. You don't even need to download Lean. You can just um, go here and yeah, and it shows you how to do stuff, and you can write proofs, learn how to use it. Do I like Langlands or AG more? This is a meaningless question. I mean, you can't, like, I don't know, you can't disentangle them. Yeah, you can't disentangle these things. So, okay, maybe it's not a meaningless question. I mean, definitely, you could be someone that just works in hard analysis and does stuff in Langlands. But I don't know. There's just inevitably, if you get deep enough about algebraic geometry, you'll probably hit on something that is related to Langlands, and vice versa. So, towards the end of the paper, there's some comments about categorical local Langlands. Interesting. Interesting. What is SH here? Category of sheaves with equivariant structure. Whoa, what is this? There's a natural equivalence between these sums of sheaves, semi-simple parameters. Huh. Interesting. Who would win in a fight? Langlands. It's an S on his name. Or algebraic geometry in their primes. Everyone would lose because the pure energy released from their battle would destroy the entire Earth. If you had time to edit Vakil, you'd call it Rising Sea Modulo Yapping. How dare you? How dare you? Facts, the amount of yapping in Vakil is insane. Okay, then go stick to Hartshorn, I guess. Go have fun reading with Hartshorn and all that he tells you. You think there's a possible nice intuition for reductive groups? If you think about the root system, then every root has an inverse. Yeah, I don't remember. Like a couple years ago when I was, studying to do my candidacy exam, I remember being like trying to, read up so I could, figured I'd probably get asked about reductive groups and spin some explanation, but I don't know. Do you think papers should have at least background references for the babies? I don't know. I don't know. My mind has changed on this over the years. I used to be more of an aggressive believer that papers should do more to welcome newcomers to the field. But I don't know. I mean, yeah, the question is, who are papers for? Really, they're for, I don't know. Yeah, it's tough. I mean, there is I don't know. I don't know the answer to that. Because you could put forward the argument that yeah, it needs to be more, one needs to do more to, make it clear to people new to the field. On the other hand, I mean, writing papers is hard. Like I want to try and do a good job, and I would like, my papers to be read by someone. Yeah, not every researcher is a good educator and vice versa. That's true. That's part of it. But I think the other part too is, like, even if you are a good educator, You know, like there's a time to educate and there's a time to do research. And yeah, I would like my paper to be, you know, I would like it to be the case that some other grad student picks it up and can like understand and learn things from it, you know, and try and point to good references. But yeah, at the same time, it's like, well, how much background do you really include? You know, um, yeah. So I don't know. I don't know. I don't really know. And I think I don't know. Yeah, I mean, it's also tough because there's lots of mixed opinions, right? If I think if you put in too much detail, which I think my the current draft of my next paper has like way too much basic detail and basic computations. I'm sure that people are going to tell me to take out some of these things, but uh, you know, experts in the field who partly you're writing to are going to be like, I don't want to, I don't want to see all these details. Like, I don't care about these basic details. You know, it's like insulting that you include it. So, I don't know. I mean, there's an interview of mine that unfortunately is very windy, and the audio is all sort of blown out. But there's an interview of mine with Adam Clay. If you go look on my channel, and we were talking about this, and his sort of solution is that he always put, you know, links to a second version of his paper, which he puts on the website that has all the, like, a lot of the gritty basic details that don't appear in the published version. So that's his compromise. Can I do the fiber product over A2 of A minus 0 with spec of blah, blah, blah? Of OA2, which is, the local ring at 0? I mean, shouldn't the fiber product, I mean, the fiber product of A2, or over A2, so the fiber product over A2 of A2 minus a point and A2 localized at a point, this should just be spec of A2. I don't know A2 if you mean like Z or C or whatever. I mean, but let's just say complex because it's easier. This will just be what? C XY modulo modulo XY. Wait, no. I removed a point. Sorry. CXY plus or minus tensor over CXY. And then the localized ring. Wait, this is just the right. Oh yeah. This is the localized ring. So then it's this CXY inverted at this ideal. I don't know. Maybe I'll put 0 here. Localized. It should just be that. So I don't know. I don't know if that answers your question. If you wanted me to work this out more explicitly, I guess one could try and draw a picture. Paul Marie, I mean, you're already jumping ahead to other crazy questions. Do I know the relationship between S duality and the Langlands dual group? No, I do not. There is no job called math translator paper to general public. Yeah. Nor should there be. Maybe it'd be motivation for newcomers to learn the prerequisites. I don't know, newcomers should want to learn the prerequisites anyways. I mean, I'm not so concerned about that. I mean, the thing is, like, there are textbooks and resources, and the job of your supervisor is to help you learn, right? So I don't know. Like, yes, it's good to keep in mind helping future generations, and I don't think it's a bad idea to try and put in more background and details, but you're stuck on this problem. Prove that every group of order 29 times 30 has a normal 29 Sylow subgroup. Yeah, well, 29, what is this? 29, yeah, localized at XY. Yeah, that's true. 29 is prime times 2 times 3 times 5. Yeah. Well, this is just, I think, Sylow 2, right? Sylow 2 basically says that there's some formula, like the number of normal subgroups. Yeah. Yeah, I mean, there's some formula that tells you something about the what the number, I don't even remember what it is, but what this is modulo some other number, I don't even remember what it is. But if you go look up Sylow 2 or 3, I should go make a video on that as well. Too many videos I need to make. But if you go look that up, you'll get something, and you should be able to conclude that there's from that there's just a single. I'm guessing this is how the proof will go. That from that, you should be able to argue that there's just a single Sylow subgroup. And since all the Sylow subgroups are, if you conjugate a Sylow subgroup, you get a Sylow subgroup back. Well, this means it's fixed under conjugation, which implies that it's normal. 29 divides 30 and is equivalent to 1 mod 29. Right. I see. Yeah, so 29, okay, yeah, n29 divides 30, so, right, so that means n29 divides 2 times 3 times 5, and what did you say, n29 is congruent to 1 or 30, is equal to 1 or congruent to 1 mod 29, right? You literally screenshot part of Hartshorn that you don't get, and ChatGPT explains it, and then it's actually really good. Yeah, but how do you know it's really good if you didn't understand what it said before? How do you trust that what ChatGPT is telling you is correct? Because you didn't understand the passage. And so how could you possibly know whether it correctly explained it or not? It doesn't make sense. Right. How do we rule out 30? Well, how do we rule out 30? But how do you know that you understand it after the explanation? Like, you can understand the words that ChatGPT is saying, but how do you know that that is the correct interpretation of the words that ChatGPT is giving you? Like, do you mean that after the explanation you were able to go and solve exercises and then have someone who knows what they're talking about verify that you proved things correctly? I don't know. Yeah, the real skill is to check ChatGPT if it's right or wrong. Yeah. You don't use ChatGPT for math questions. You just wait until K-Theory stream starts and ask your questions here. Good. Good. Although I don't know if I can be right as often as ChatGPT. So me and ChatGPT might be comparable. Other professional mathematicians are probably better. How do you even... Yeah, exactly. It can explain the wrong thing correctly. Yeah, exactly. So, yeah. I'm not saying don't use it, but, like, be cautious and take your own understanding with a rock of salt. Okay, why can't it be 30? Why can't it be 30 in this case? Why can't there be 30? Yeah, I don't know. Maybe try something with the class formula. That's what I would do next. Think about like your conjugacy classes. That would be my next go-to. But I need to go. I need to go get some work done. Hit the gym, chest day, and then he tried counting elements, but it wasn't enough. Yeah, orbit stabilizer. Yeah, use the class formula. Use the class formula. That's what you want. I'm sure it's in the class formula. Yeah. I mean it's that makes sense. Edit Smith. Yeah. I mean, yeah, you can use it as a tool like that, but always take everything with skepticism. I mean, as a mathematician, you should always take everything, including your own understanding, with a dose of skepticism. The Sylow subgroups would only intersect at the identity. Because we have distinctness of primes. That's true. That is true. But I should go. So I'll see y'all tomorrow, and maybe we'll come back here, and keep discussing Sylow. So I'll see y'all then.